Whoa, you guys are quick today. Oh, okay, I got Kiara, Matthias, and Zach, and Alicia. Holy smokes. Alicia, Zach, Kiara. You kind of snuck up on me there. Kiara, Matthias. I'm trying to mark y'all down. I got Inessa, Aaron, Malta, Ethan. Whoa, I got Jack, I got Clara, I got Timothy P, and I got Stella. I got Lauren. I've got Julius, Hannah, and Alessandra. Still hurrying here. I've got Sophie, Sina, and Ingrid. Sophie, Sina. Man, you guys are quick today. I've got Kai, I've got Alessia. I'm trying to write y'all down. Isaiah, gotcha. Felix, and Corsine. Good. Keep them coming. Hey, I got Paul. Good. Isabella and Leo. Great. I got Alessia, I got you. I got Liam, Corey, and Ayala. Still getting you down here. I got Michael and Isaiah, I got you already. Michael and Aslan. Good. All right, let me check a few. Oh, there's one more. I got Linus. Linus, good. Okay, do I have Tim Hartling? Do I have Tim? Do I have Abram? Do I have Ali? Do I have Amelie? Do I have Charlotte? Do I have Isaac? Do I have Devante? Do I have Anton? Do I have Cassidy? Do I have... That's it. I got everybody else. Good. There's a couple more. Paul, I got you already. Charlotte, I got you now. Still looking for Tim H, Avram, Ali, and Amelie. And from my 9E, I still need Isaac, Devante, Anton, Cassidy. Any of you there, please let me know. And I don't see the rest of you. Okay, here's what we're up to today. Two things. I graded your assignment. Some of you didn't do it. Be sure and do the next one because a 0's not a nice grade. Those that did it did pretty good, but there's a few bad habits. We're going to try and get rid of those before we go on to half-life problems later this hour. Good, I got a couple more. Thank you for checking in. I got Amelie. I got Anton and Isaac. That's great. Good. Okay, I'll set this aside because that's the vast majority of you folks. And I'll set this for my other class back here because you don't need that. Good. Charlotte is here too. Thank you. I got Charlotte. Yeah. Thank you very much. Avram's connection is bad. Okay, thank you. Then you share stuff with him, Aslan. I'll mark him in. Thank you for telling me. Yeah, gotcha, Amelie. Thank you. Devontae can't get to the video. It's unavailable for him. I don't know why. Everybody else has gotten to it. Tell him to try again there, Kai. Please have him try again because I got 35 of you on, so I know it's very possible. Oh, 36. Okay, you ready? All right, let's hit it. Devontae made it. Okay, good. Almost everybody. Hot diggity dog. Hot diggity dog. Okay, so here we go. I'll leave that over there. Let's warm up. You're on your phone. Sorry you have to do that, Devontae. You may want to watch the video later because it'll be hard for you to see all this on your phone. I'm sorry about that. What a bummer. Okay, so alpha, beta, gamma. Let's do some. I don't have the assignment with me, so we're just going to start one, and I'm going to grab one and say, okay, so PB, and that is 82. And I'm going to make something up here. I'm going to say 204 goes to alpha plus. Now, bad habit. I got some of you that are putting a line here. It's not a fraction. Get that out of there. No lines there. It's two different numbers. That's the number of protons, the atomic number. The top one is the mass number of protons plus neutrons. There's no line between them. Don't do that. It's not math class, okay? So it's two different numbers. Okay, if I got alpha, let me know the numbers and who this is here. Okay, now let's do a beta. So I'm going to, again, just pick one at random. Let's pick W. That's a nice letter. W, I got, let's say, so that's 74. And the top one, let's put, I don't know, let's do 180. Okay. Okay, so, and let's say you got a beta. And I want to know what you get. Okay, my people, let's call this A. Let's call this B. Can you give me some answers? So please give me the numbers and what element it would be. You'll need your periodic table today, my people. So please give me the numbers and what element. Okay, I can write the symbol alpha, or, and Alessandra brings up a good point, I can write a helium nucleus if you don't want to write this little alpha symbol. But if I do this, here's what I got to write. Helium 2, 4, 2 plus. If you're going to write it this way, you got to have the 2 plus there to show that it's not got any electrons. So I'll write or this. So you can write an alpha as that or that. Okay, so what's the other thing left? Good. I got 280 and good. I got 80. So I'm taking 2 out there, and I got 200. Thank you. Good. Thank you, Inessa. Thank you, Kai. Thank you, everybody I missed already because I'm so slow. Kiara and others. And the top number is 200. And so they are all right. This is 80. So it's mercury. For those that can do these, I'm very glad. It looks like you have good confidence. By the way, in words, I can say, you ready? I'll put a little star here. This is called mercury 200. Or I can write Hg 200. That's when I'm talking about it. I can say it. Well, I got mercury 200 here, Hg 200. That's the name of the isotope. So the isotope is called mercury 200 or Hg 200 or whatever, okay? But that's the symbol right here. So most of you got that. Good. Let's do the next one. Wow, lots of good answers. Thank you, everybody, for participating. Got it from Leo and Lauren and lots of you. Super. Let's do the next one. Allie is here. Thank you for checking in. Allie. Let me mark him down. Voila. Okay. All right. Good. So here we go. This is 74 and 180. It's beta. So what's going to be my numbers here? Ooh, some of you are quick. Alessandra's got something as well as Sina already. And they're saying that the top number is still 180. And the bottom number is bigger now, 74. No, 75. Remember, beta is the weird one, right? If this is my neutron, it changes into a proton and an electron flies off. That's the beta particle. So you can put a beta particle or you can put E minus if you like. Good. And a lot of you have the element. 75 is Re. That's right. Well done. Thank you. Okay. Questions from all of you. Some of you also did not have success getting the right numbers. Remember, this alpha you have to subtract 4 and 2. Beta, I've got to add 1 because a neutron changes to a proton. So it becomes a bigger number, 75. Good. Thank you, Jack, and everybody else for participating. Question in general, what happens to the numbers if it's gamma radiation? Who remembers? What happens to the numbers if it's gamma radiation? Yes, Aslan, you may. What happens to the numbers if it's gamma? Thank you. Nothing at all. They stay the same. Exactly. Thank you, Corey, Inessa, Alexandra, and others. Dynamite. Okay? Questions from you about that now? If you missed something, oh, everybody got that. If you missed something here, ask me if you still have a question. By the way, if I ask for a nuclear reaction, you have to have an arrow and you have to have the stuff on both sides. Some of you just want to put this as your answer. I want the whole thing written if I want a reaction. Okay? Any questions before we start something new? All right. I'm taking that as a no. Good participation today, gang. Keep it up. Appreciate it. Okay? All right, I'm going to erase here. Here we go. Okay, we had this last time, but we really have to review something before we go on. Tim, the long lost Tim is here. Tim H is here. Okay, thank you, Tim. Tim H, you got to go and watch the rest of the video, though. You're rather late. You missed a bunch. Alessia, you may write just for alpha, you may write the symbol alpha. Or you can write HE with 4 and 2, but you have to then put a 2 plus. You may not skip the 2 plus if you're going to do this. Or you can use, as Alessia asked about, just the symbol alpha. That would be fine. Yes, I got you, Timothy, already. Okay. Good. Any other questions before we begin with something new? Okay, here we go. Ben. We talked about a half-life being from last time, right? It's the time for half of a mass of radioactive isotope, whatever it is, I know that's getting hard to read. I got to renew my blue, to decay to something else. And next time, and last time we also said, hey, if this is time, and if this is my mass of the isotope, then this decays over time. Let's say this is 10 grams. So this is grams. Well, if this decays over time, I got less and less and less and less. We say it's an exponential decay. That's the math term. And if I go down to 5, and I go out here, then that, my folks, will be the half-life, won't it? So what I'm trying to show you is you can get this from a graph. So I'll answer questions in just a moment. So if I got a graph of mass and time, I can take half of my starting mass. So let's say I go from 10 down to 5 grams. And at 5, I go over, hit my graph, and go down and find the time in whatever it is, seconds, minutes, years, depends on the substance, doesn't it? Okay, I know I got some questions. What does it say up here? It says halftime is, oh no, okay, I forgot a word. Sorry. Half-life, sorry. Please put that word in. I got too excited. So the half-life is the time for half of a mass of radioactive isotope to decay to something else. Let me say that again. So the half-life is the time for half of a mass of radioactive decay to decay to something else. In my graph, if I have 10 grams, then the half-life would be when it's at 5 grams. Or I could go, the half-life could be when it goes from 5 down to 2.5. You know what I mean? It's half of whatever I start at. Okay, anything else we've got here? What about beta reactions? Alessia, I'm not sure I understand your questions. Your question. I don't know what you mean by what about the beta reactions. For beta, you use beta, or you can use an electron. Yes, Kai, that's right. If that's what she means, right, you can use beta or an electron for the beta particle. The beta particle, an electron, or big B for beta, or the German Eszett looks about like a beta. Yeah? Okay. All right. Let's do a problem with some numbers now, and you'll see how I want you to go about this, how you have to go about it. Okay, here we go. Okay, I'm going to make something up. So I'm pulling the numbers out of my head. Okay. All right. Example. 42 grams of uranium, I'll say 241 has a half-life of 2.1 million years. How much radioactive U-241 is left after 9 million years? Okay, now I may write some of you because there's a math formula that you can do this with, but it's 10th grade math. So if you're good in math, you can look up the exponential decay math method to find this. But for most of you, I want you to learn a different method instead, and that's using a chart. So use a chart. You ready? Here's the chart. Okay, number of half-lives, mass of isotope, time gone by. And this would be in years. Okay, because we've got years for this half-life. Okay, now let's look at our question, okay? How much of the radioactive sample is left, U-241 is left, after 9 million years, okay? Here we go. First number of half-lives, none, 0. When 0 half-lives have gone by, in other words, that's when we're starting, what's our mass of the isotope? Just so I know you're following. At time 0, in other words, right when I start the clock, how much do I have of my radioactive isotope? What will I put here? Thank you. Inessa, Zach, and lots of others. Ethan, good. So I'm starting with 42 grams of it. Okay? Time gone by, 0 years, gang. It hasn't started to decay yet. Now, start the stopwatch. Here we go. After 1 half-life has gone by, mass of the isotope that's left, let's see if you're following now. So let's say 1 half-life goes by. So what was the half-life? 2.1 million years. How much of the 42 grams will be left after 2.1 million years? Yeah, great. Aaron's got it, Kiara, and lots of others, Sophie as well. Good, half of that, 21 grams. Is it that easy? Yes. Let's go to another half-life. We want to go to what? 9 million, so we're not there yet. Okay, another half-life goes by. So that's what? Now we have 4.2 million years have gone by. How much is left of the 21 grams? All right, Aaron's got it, and Alessia and Sophie. I got some quick minds too today. Alessandra, it is indeed 10.5 grams left. Is it that easy? Just cutting stuff in half? Yes. Now, I'm going to try and catch you. 3 half-lives go by. How many millions of years is this? 3 half-lives go by. How many millions of years have gone by? Think carefully. No, you're answering the wrong question. How many millions of years have gone by? Now some are answering the right question. Thank you, Kai and others. And they're right. There's 2 answers. One is right and one's wrong. So watch this. It's 6.3. I have to add another half-life. 6.3. So 6.3 million. And then, of course, most of you got this already. It's like 5.25 grams. I know I'm kind of running out of room, but I think we just got just about enough here. 4. How much time has gone by? How much time has gone by after 4 half-lives? You've been ignored. Sorry, Liam. I'm not trying to ignore anybody. Okay. Thank you. Thank you, Aslan. So I got, oh, Aslan, that's too big. Careful. What? Look at your number. I don't think it'd be 88. We got to add what? Add a 2.1, right? So it'll be 8.4. Thank you, Kiara and Corey. And thank you, Liam. Thank you, Liam. Okay, so how much is left here? Half of this would be what? Some are already answering it. Thank you, Aaron and others. 2.62, let's just round it. 2.62 grams. Now look at the answer to my question. Well, okay, it's 9. What if I go one more half-life? It's going to be too much. So here's what you can say as a 9th grader. You're going to say, okay, well, let's just do 5. Okay, 5. So it'd be 5 half-lives would be what? 1.3 grams, and it'd be 10.5 million years. So let's answer the question now. How much radioactive decay is, how much radioactive U-241 is left after 9 million years? We don't know for sure, but we're going to use our chart and kind of say, well, it's between what? It's between 2.62 and 1.3. Can we estimate that? It's probably a lot closer to what? A lot closer to that, wouldn't it be? Because 10.5 is, that's 1.5 away from 9 million. And this is about 500,000 away. So we could say our answer a bit less than 2.62 grams of U-241. In other words, as 9th graders, I'm going to ask you to kind of estimate and then give your answer based on your chart. Or you could say that, Leo, around 2 grams, maybe a little over 2 grams. But certainly it's going to be something less than 2.62 grams. So you're going to give an answer based on your chart. I don't want you to just guess. So if you see this on a quiz or test someday, which I hope you will when we're back in school, then I want you to do a chart to show your work like this. Alternatively, if you're good in math, you can learn how to use the formula, but it involves some 10th grade math, okay? So depends on you. But if you want to use the math, I may contact you if that's something I think you can do. Okay, here we go. Whew. I wonder if you guys have had as many live streams as I have today. We doing okay on time? Yeah, we got time. We're going to do one more together here. And then I'm going to assign you an assignment to have you do some like this, okay? All right, so another example. A bone containing carbon 14 is analyzed to determine its age. Is it Stone Age? In other words, greater than 10,000 years old. Here's the data. Okay. You need to know the half-life, don't you? So the half-life for carbon, and here's how we write it. C, the half-life, well, do I want to write like that with you? No, I don't. Carbon, I'll do it this way. C14 half-life is, we're going to round it because this one I do know. It's an actual method of dating things that have carbon in it, organic things like bones and trees and stuff. It's about 6,000 years. You're allowed to use that. The actual is some 5,800, blah, blah, blah. We're going to use 6,000 years because it's easy. Okay. From 1.0 initial gram, or initial mass of C14. And I'm picking 1 because it's a nice number, okay? So 1.0 gram, 1.0 grams of initial mass of C14, 0.04 grams is left. So obviously we want to figure out what? We want to figure out how old this is. Yeah, Ethan, you could round it to 2.5 grams. That'd probably be fine too. So we're trying to find its age. Make a chart, okay? So number of half-lives. Doesn't matter what order. Time passed. And mass of carbon-14. And that's in grams. And the time passed, let's just put the label up here, years. Have your science teachers already taught you this? If you put the label in the top of the column, you don't have to put it every time below. So if I write years up here, I can just write the number here. And if I write grams here, I can just write the number. All right? It saves time. It's what all scientists do. So number of half-lives, well, let's start with 0. And the mass was starting at 1 gram. The time passed 0 years. Okay, you ready? Why don't you guys work on it for the next 2 minutes? Yes, yes, you could. So why don't you guys work on it for the next couple minutes and see if you can do it. So do it on a little piece of scratch paper, wherever you're taking notes, okay? I wish I could have one of you come to the board and write it up here. I'll make some lines while you're doing that, okay? Ready? Maybe that's enough. We'll see, huh? No, it's not enough. You gotta go more. We may have to do more up above. We'll see. Okay? Okay, I'll start you off here. Hopefully you put some half-lives that have gone by. 1, 2, 3, 4, 5. Could somebody list the time passed? What did you put for the first? What did you put for the first 5 half-lives? Could someone type it in for me? What do I get here for the time that has passed? I ask this because sometimes students make mistakes here. So what did you get for the first, after the first 1, then 2, then 3, then 4, then 5? Could somebody type in their 5 amounts of time? Good. Alessandra is on the case. She's got 6,000. She's got 12,000. Good. And Kai has a bunch of them. Kai, 6, 12, and now 18,000. Let's see if others have the same. Yes, and Aaron had that as well as Alessandra. So thank you. And I'm going to go back to Kai. She's got 24,000. And now the last one. Let's see if someone has the last one in there. Aaron does, and I lost Kai because the board went too high. Liam has it as well. Thank you, Liam. So we got 30,000. Okay, good. I put in some commas in the English American way. Okay. All right. What about the masses? Somebody want to give me their masses they've got? The first one is 1 gram. Okay, that was starting with 1 gram. What do you get for your masses? I got down my chart. Thank you. Isaiah had it in there too. Thank you, Isaiah. What are my masses? Go ahead and punch them in. Thank you. There's Kiara's got the first 1.5. Right, I don't need grams because I put it in the column. So 1.5. There's a bunch from Kai. 0.25, she says. And Alessandra has the next, as does Kiara, 0.125. Another after that, we got 0.06, 0.062, and then we got 0.031. Thank you, Kai and others. 0.031. I just wrote that wrong. So 0.031. Good. Let's see who else had that too. Thank you, Tim H. And Aaron had a bunch of those. Charlotta had some of those. Thank you. Good. So did Kai and Paul. Very good. So I think we can answer our question now. Well, it's age. It's going to be. Oh, no. Can we get that far? Let's see. 0.01. We're not quite there, are we? We're not quite there. We got to go one more. I'm going to do it up here. You can do it down below. We got to do 6, don't we? 6 will be what? 36,000 years. and then it would be 0.015. And what did we have? 0.014. Oh, so we're about there. Okay. So what can we say is our answer? Yeah. So answer, the bone is a bit more than years old. So who's following? Who's following? So what's our conclusion, folks? The bone is a bit more than, look back at the data. Want to get to this number, right? We're about there. Super, good. So a bit more than 36,000 years old. And Stone Age is greater than 10,000. Could it be? Yup. Bone is definitely Stone Age. Definitely. We should say from the Stone Age. That's how they'd say it, archaeologists. It's old. Pretty cool, huh? That's how scientists actually tell the age of stuff. Now, they use a formula that you'll learn next year in 10th grade, but they use this same idea with radioactive isotope and how much is left from carbon-14. Pretty cool, huh? Because you ever hear like, oh, this tree is this old, okay? Well, trees, you can also count the rings if it's still alive. But if it's just like a piece of wood under the ocean that has been maybe buried for a long time, then they have to use carbon-14 dating. That's what they call the technique. So you've learned about this technique, carbon-14 dating. So it doesn't mean going out to like the movies on a Friday night, right? It means figuring out how old things are. Okay? Cool. Questions from you? That may be the best participation I ever had. You guys really rocked it today. Thank you so much. There's Avram Israel. It is 100% accurate. You know, Avram, it's really accurate until you get beyond about 200,000 years. It's a good question. Once I get beyond 2,000 years, it's just too old, and there's too little of the isotope left. For dinosaurs, which are like 200 and 300 million years old, I can't use it. So there are limits to what I can use carbon-14 dating for. It has to have carbon in it, and it has to be like 200,000 years old or younger. Thank you. Good question, Avram. Yes, Ethan, as long as it has carbon in it. If it's like a piece of steel or something, no. It has to have carbon in it, organic material, we say. Mm-hmm. Good. Any other questions from you? I should write what Avram said. So good for up to 200,000 years old. All right. From Avram's good question. If it's older than that, forget it. It's just too old. So they use it some of the age artifacts. Yeah. Behest? Sorry, Alessia, I'm not following you. Yeah, so the technique, carbon-14 dating, good up to 20,000 years old. Good. Okay, that's it, gang. Thank you. And I'm going to send you an assignment to practice some of those this week. And I'll see you later in the week for some other stuff on nuclear physics. Good. Have a good rest of your week. Stay safe. Hope to see you soon. Bye-bye.